If you're like me, you've probably seen these words on the internet and thought, wow, those terms seem awesome. And you're right, they are really cool, but the things you read online about them really overcomplicate the concepts to the average person and make it hard to understand, which sucks. Well, fear not, because I'm going to teach you about these crazy cool ideas in physics in under 10 minutes each in a way that anyone can understand. If you only want to learn about a specific one, here's the timestamps for each. Okay, we're going to go in order of most real to most theoretical, because these fall on a pretty wide spectrum. Let's start with antimatter. I only ever heard this term as a kid in sci-fi shows and sci-fi video games, and I always accepted it as this like science fiction idea, something that a writer came up with somewhere, but of course it didn't actually exist. Come to find out, when I began studying astrophysics, that not only is antimatter real, but it's not uncommon, and it's really cool. To understand antimatter, though, you need to understand matter, and don't worry, we won't go too deep on it. If you've taken a chemistry class before, you probably understand the concept of an atom and its parts, what we call the standard model: protons, neutrons, electrons, all that good stuff. This is typically the smallest unit of matter, aka stuff, that they will teach you in basic science classes. But in fact, these particles are made up of even smaller particles, what we call subatomic particles, below the atom level. You don't need to know anything about them, just know that this is where the difference between antimatter and regular matter lies. For example, say an electron is composed of some subatomic particles. I'll call them BLT for bacon, lettuce, tomato, and each one has its own charge. Well, an anti-electron, the antimatter version of an electron, has the exact same parts, the same BLT, but they have opposite charges. What the subatomic particles are isn't really important, but the antimatter equivalent of an electron, which we call a positron, just has identical subatomic particles in every way except for the charge. So, this antiparticle is essentially just an electron with the opposite charge. It has identical weight to an electron, identical spin to an electron, and it behaves, as far as we know, identically to an electron. But instead of being negatively charged, it's equally positively charged. These same antiparticle versions exist of protons too, called antiprotons, and the concept is the exact same. Same weight, same behavior, opposite charge. Now you might wonder, okay, if antimatter exists, where is it? Why don't I hear more about it? Well, the visible universe as we know it is dominated by regular matter. The standard atoms that we think of make up our everything, and for antimatter, there's just one kinda cool problem. When antimatter collides with its regular matter equivalent, it leads to annihilation, where both particles are destroyed, and there's a big burst of energy, and a bunch of subatomic particles are released. It's pretty intense. Now, you might think this would just happen occasionally by random chance as things sort of move around, but remember, antimatter particles and their matter equivalents have opposite charges. So an electron has a -1 charge and a positron has a +1 charge, and opposite charges attract each other. So for example, if I created an antiproton directly in front of me right now, in an immeasurably small amount of time, it would find a regular proton and annihilate. Before you could even notice it was there, boom. And in fact, this happens both naturally and artificially. Our bodies are producing and annihilating antimatter as we speak. Many types of radiation cause antimatter, such as potassium radiation from bananas. We've even purposefully created antimatter in particle accelerators, these awesome, giant, expensive machines that speed particles up really fast. We crash some stuff into some other stuff, and we made antimatter. Typically, though, the moment that it's created, it'll just hit the wall of the accelerator and annihilate. Now, we have managed to trap antimatter before. We can use magnetic fields to keep it away from its matter equivalent, keep it from annihilating, so it can't find another particle to crash into. While we've only trapped small amounts, and I mean literally single few particles at a time, for a small amount of time. I think the record is 2 months, which is pretty good, but for the most part we trap it for a couple seconds. We have created and observed antimatter. So now the most pressing question is, what good is antimatter and what can we use it for? Why do we need to care? Well, if you're a simple-minded person like me, and the idea of explosions sounds cool to you, you might have thought about how we might harness the energy that is made when antimatter annihilates with regular matter. And many scientists and engineers have thought the same thing. There are many, many models out there for spaceships, rockets, and more, which are conceptualized with antimatter as the fuel source. Essentially, the idea is we shoot individual particles of antimatter at some regular matter and use the force of the explosion to propel us forward. And if you ignore the creation of antimatter, this idea is really good. Energy from annihilation is huge compared to the particles put in. Don't get me wrong, if antimatter hit matter right in front of you right now, you wouldn't even notice. But for the size of the particle, the energy that's released is pretty significant. So this could be an incredibly efficient fuel source by size. And this is where science fiction gets its ideas of antimatter, a lightweight, absurdly efficient fuel source powered by mini explosions. It's pretty cool, right? And you might be wondering why we don't use it then. Well, surprise, surprise. Remember how I said if you ignore the creation of antimatter? Well, in the real world, you can't do that. And creating it is obscenely expensive, like incomprehensibly expensive, like entire government's yearly budget level of expensive to make one atom. It's pretty insane. Building and operating particle accelerators is no normal lab operation, and even if we could somehow efficiently create antimatter, how do you store it? I mean, you need giant magnetic fields to trap single particles at a time, keeping them away from regular matter. And those magnets are expensive, they require a lot of electricity, and also we've only really used them to trap one or two particles. The amount that you would need to use it as a fuel source would make it expensive and a logistical nightmare. So yeah, all the antimatter we've ever created could fit in a space smaller than you can see, and barely any of those particles existed simultaneously, so it's not exactly a reliable fuel source, although the idea is cool. So what good is antimatter? If it comes into existence, blows up instantly, and disappears, why do we care? Well, the answer to that is kind of complicated, but again, if you've taken basic science classes, you might be confused by now why the universe has so much matter and so little antimatter, and we are too. After all, due to our laws of conservation, which dictate everything in the universe, when a particle was created during the Big Bang, its antiparticle would also have been created. Meaning, when the universe began, there were equal amounts of matter and antimatter, if only for a moment. So where did all the antimatter go? How does it make sense that the antimatter disappeared, but the matter didn't? And for that matter, why didn't the two particle types, when the universe was all confined into a tiny space during the Big Bang, simply just collide with each other and annihilate, leaving us with no matter at all? These are open questions, and solving them is completely reliant on expanding our knowledge of antimatter. Learning more about antimatter could mean better understanding how our universe formed and functions, and that's why we study it. Okay, I hope that was understandable. I want to strike a balance between making things easy to comprehend without taking away from the meaning of the concept. Let's go ahead and talk about dark matter. Okay, dark matter. Dark matter is slightly more abstract than antimatter, and it's not to say that it doesn't exist, because it is, well, dark. We can't directly observe it. However, there's a lot of evidence that it exists. Essentially, dark matter is matter that doesn't follow our rules for regular matter or antimatter in some way, leading to it not reflecting light. Therefore, dark matter is invisible. And that sounds like science fiction, I know. There's a bunch of matter out there that's invisible. But if you don't know, the way that we see, and really how anything sees, is that light created by stuff like the sun bounces off objects and back to our eyes. Based on the way it bounces, we get different colors, but that's how we see stuff. Dark matter just doesn't reflect light for whatever reason, so we can't see it. For that reason, we're not really even sure what it's made of, so if we can't see it, how do we know that it exists? Well, this is where the idea becomes a little abstract, so bear with me. At some point of our maths, models, and understanding of the universe got better and better, our margin of error got smaller and smaller. For example, take a measurement that we would have had a long time ago, like the width of the solar system. We used to have a measurement of the width of the solar system plus or minus a really large amount of space because our math was imprecise. But when the math got more and more precise, we got to a near exact measurement, and that plus or minus became very small. Our margin of error in our math became very small. And somewhere along that way of improvement, we started to notice that when we observed orbits or gravity of these large masses in space, they didn't exactly match how we thought they would. These aren't huge deviations, mind you, but enough that when the math is really precise and you know that your margin of error is small, you can tell that something is wrong in the models of the universe. We're missing a piece. And this is where dark matter comes in. If we theoretically, in these models, assume that there is additional matter out there in space that we can't see, it fixes our models and makes our calculations line up much more closely with what we actually observe. So, we can look at, for example, how one celestial object is orbiting another, and calculate how much non-visible matter would have to be there for our equations to equal what we're actually seeing and measuring with our eyes. This correction in our models is dark matter. What's it made of? We don't know. Why doesn't it reflect light? We don't know. Is a matter-like substance even the correct explanation for this margin of error in the calculations? We're not like 100% sure, but the current working theory is the theory of dark matter. There are many tests and papers which use dark matter to get more precise and accurate calculations. So at the absolute minimum, it is close enough to what's actually going on to be useful to physicists as a concept. Notably, dark matter is actually the dominant matter type in our universe, outnumbering visible matter by 20 to 1. This seems absurd, admittedly, that there's 20 times as much invisible stuff as there is visible stuff, but the universe doesn't conform to what we think is absurd and what we think is reasonable. And that's about it for dark matter. Until we find a way to capture it or remotely determine what it's made of, it will just exist as a theoretical solution to our models of the universe that we can't quite see. Okay, we're diving deeper into the depths of physics now with dark energy. If you understood my explanation of dark matter, first of all, congratulations for understanding me, but second of all, you probably think you know what dark energy is. Yeah, dark matter is invisible matter, so dark energy is invisible energy, right? Well, smart guy, can you see heat energy? And no, I'm not talking about like the little ripples that are caused by a hot day on asphalt. I'm talking about heat energy itself. Can you see chemical energy? No, I didn't think so. So, dark energy is named that way because it has a similar function in our math to dark matter, not because it's specifically invisible, though it is. So, let's talk about it. As a concept, dark energy is quite simple. To understand it, though, you first need to understand gravity, which is sort of its opposite. Here's the equation for gravity. Oh god, equations. I know, don't worry. It's really simple. What's important is what contributes to gravitational force and how it contributes. In the equation, we can see that for any two objects, their gravity is their masses multiplied, divided by the distance between them squared. For our purposes, you can ignore the gravitational constant. What this means is that if two things are bigger, aka have more mass, the gravitational force goes up, the pull goes up. And if they're further away, aka more distance, the gravitational force, aka the pull between them, goes down. It's pretty intuitive. Large, close-by things will pull on each other more than small, far-away things. So then consider this. Everything in the universe has some gravitational force between each other. You, watching this video, and me, even though you might be on the other side of the Earth, we have a gravitational pull towards each other. Or even if you're an alien watching my video from a distant galaxy, we can plug our masses and distance into this equation and we will get a gravitational force between us, albeit an incredibly small and irrelevant force. But planets, stars, and heck, even solar systems are not as small and insignificant as us. Solar systems or galaxies might be far away from each other, but they are unfathomably massive. So they have a relevant gravitational pull on each other. So if this is the case, is everything in the universe slowly getting closer together because of gravity? Well, no. And if we just cared that things are getting further apart, the explanation is really easy. It would be that the Big Bang created a massive burst of energy, sending everything outwards, and that's why everything is moving away from each other. But if this were the case, and all the stuff was spreading out from one initial push, it should, over time, slow down, especially when you take into account that everything is pulled together by gravity. The universe can be expanding from the momentum of the Big Bang, yes, but gravity should be slowly reducing that rate of expansion as stuff is pulled together, leading to a point where the universe will eventually stop expanding and start shrinking. There's only one problem with this theory. We have observed, via some complex space experiments related to distant supernovae, that the universe's expansion is not slowing with time. Not only that, it's not even staying the same. It is actively expanding faster and faster all the time, to the point where the stuff on the edge of the observable universe, basically as far as we could possibly see, is moving away from us at the speed of light or even faster, meaning that we will never be able to see the light that it's emitting because it can't get to us. Quick side note, I know people will be in shock and awe at the concept that something is moving faster than the speed of light, but think of it this way. The objects at the edge of the observable universe are not moving through space faster than the speed of light in the same way that we are not moving through space faster than the speed of light. It's just that the expansion of space between us, the void between us, is pushing us apart at a speed faster than light. So we're all good. We didn't break the laws of physics with this one. Okay, back to dark energy. So, if the only forces affecting the universe are the ones we already knew, we have no explanation for why the universe would be expanding faster and faster, instead of slowing down because of gravity. Therefore, the obvious conclusion is that there's a force we haven't yet observed, which is pushing outwards, basically doing the opposite of gravity. And this force is what we call dark energy. Dark energy is thought to mostly exist in small but uniform amounts throughout the vacuum of space. In areas where there's a lot of gravity, such as within our solar system, dark energy would have no noticeable effect. The gravity is simply too strong between us and our sun for any dark energy to affect that pull. However, outside of solar systems, and in the dead space between galaxies, dark energy is strong enough to push galaxies away from each other at a rate greater than gravity can bring them together, thus expanding the universe more and more. Just like dark matter, dark energy is a solution to a problem in our observations about the universe. We don't know exactly what it is or how exactly it works, nor can we observe it or say for sure that it is the explanation for what's going on. But we can clearly tell that something like it must exist, or we would see different results when we looked out into the cosmos. Okay, time for string theory. This is the one we all heard a lot about in the news growing up, and it's still brought up in sci-fi a lot. Let me first tell you what it is, then we'll talk about why it's relevant and why people care, and then I can let you down softly about why string theory isn't all that great. Okay, so first up, what is string theory? Now, ironically, this is probably the most complicated one to get a basic understanding of, but I'm confident that I can science communicate this to you. If you didn't skip the antimatter section of this video, you'll know that the particles in atoms like electrons, protons, and neutrons are not in fact the smallest particles in our universe, and that there are subatomic particles which are even smaller that make up the particles in our standard model. Well, I'm sure this is a surprise to no one, but subatomic particles have to be made of something too. I guess that's subatomic particles. We don't really know what the things are going on at this level, but at some point you keep getting smaller and smaller parts, right? I mean, everything has to be made of something if it has some properties. Until eventually you get to the most basic building block of the universe, the absolute smallest part that is making up all of the other parts. The obvious conclusion is once you get small enough, you're left with just a dot. A point in space. It's dimensionless. That's a weird thing for you to wrap your head around. I mean, you know, something has 2 dimensions, it's 2D, that means it goes in 2 directions. It's 0-dimensional. It is just a point in the universe, the absolute smallest space possible with no dimensions whatsoever. It doesn't have a width or a height or a volume. And theoretically, this dot would make up all of these subatomic particles. It would be a subatomic particle that makes up the particle above it that allows this chain reaction. And we call this a point-like particle, and has historically been what physicists assume was all the way at the bottom of the matter pyramid, if we could ever possibly observe something that small, that is. String theory proposed the idea that instead of these point-like particles making up everything, what if the smallest unit of matter was instead one-dimensional? Not 0-dimensional, one-dimensional, and it was called a string. It has a length, but no other dimensions. That's why it's one-dimensional. It is essentially a line. It's a cool concept, and it was certainly a novel idea. However, anyone could say that the fundamental basic building block of the universe is any shape. I could say that it's a 2D square at the bottom of the universe. So why do people care specifically about string theory? Well, this has to do with quantum mechanics and gravity. You don't need to understand either. All you need to know is that our current understanding of gravity doesn't work on small scales. On the order of planets and moons and stars, our model of gravity works great. We can predict something using equations and then observe nearly that exact thing in our real universe. However, once you get down to the subatomic level, this same theory of gravity just doesn't match with what we observe. It can thus be said that quantum mechanics and gravity as we know them conflict with each other. Therefore, either only one is true or neither is true. And that means our current accepted understanding of the universe is not a theory of everything because it conflicts with itself. It cannot possibly be the explanation of everything in the universe. It's very convenient to use the point-like particles for 99.99% of what we study, but we also know that something is wrong. String theory does not have this conflict. String theory is based on quantum mechanics and quantum gravity, and exists harmoniously with them. Therefore, string theory is a viable candidate of everything. If string theory is true, quantum gravity can be true too, making string theory a realistic candidate for an explanation of our entire universe. It's pretty cool, right? And then that's what everyone got so excited about. It is a theory that could potentially explain everything we observe in our universe. It seemed like we might have realistically figured out how our universe functions on the most basic of levels. For a while, there was a huge boom in string theory. String theorists were celebrities. They wrote books, they did tours, they got professor positions easily, and much more. But as time went on, everyone slowly realized that string theory is not a theory. Now, normally when someone says, this thing is not a theory, they mean it's a proven fact. But in this case, it's unfortunately the opposite. To be a theory, an idea needs to be testable. String theory, by no human measurement, is even remotely testable. Even if we imagine the most advanced level of technology and precision that tens of thousands of years into the future could bring, we could still never test string theory. In addition to being untestable, issues started to come up with the mathematical execution, particularly in particle physics, where let's just say string theory creates kind of a mess. For this reason, string theory has been demoted, and is really not a theory, and is considered by many physicists to just be an unsatisfactory explanation of the universe. Although it is uniform, it doesn't seem to be correct. We can't be sure though, and still, the advent of string theory was a huge moment for physics in the public eye, and it inspired a lot of actual mathematical advancements that have furthered our actual understanding of the universe. And the idea is still really cool to learn about and to try to wrap your head around. There's even superstring theory if you really want to break your brain, but in the modern day, string theory is, for now, pretty irrelevant. That's it for this astrophysics video. I hope you enjoyed and you learned something. If you have any further questions, I highly recommend reading the papers which study and test these concepts. There's a high barrier of entry to scientific reading, especially in mathematical disciplines like physics. But if you take it slowly, I believe you can start to get through papers and understand the really cool research that's being done as it comes out. Then you don't have to wait 50 years for some bozo like me to try and science communicate it to you. Thank you for watching, and have a great day.